Welcome to our demonstration of the motor effect. What we have here is a horseshoe magnet. The red at the top represents north and the green at the bottom represents south. And of course magnetic fields always run from north to south. So these arrows, represent or show the magnetic field direction, which is down. Now remember, the third left-hand rule says that if you put your thumb in the direction of electron flow and your fingers in the direction of the magnetic field, your palm will point in the direction of the force acting on a wire. So let's take a look at this using the third left-hand rule. Electrons move from the negative terminal of this battery on the left. They move through the wires into this little ring called a split ring commutator. This is a split, and you have one side of the commutator here and another side of the commutator going into the positive terminal. The electrons enter the commutator and then they go along this wire through the magnetic field at this point, where it's going to be perpendicular to the magnetic field. Using the equation F is equal to BIL or LBI, we could figure out the magnitude of the force. In this case, we just want the direction using the third left-hand rule. And of course, the direction is going to be to the right. If you look here, we see the Lorentz force is to the right. And as the electrons move along this path, they go parallel to the magnetic field a little bit, and then they come back towards the positive terminal. They're moving in the opposite direction. The force will be to the left, or as this black arrow shows, in the opposite direction to this. So that's what keeps this rotating in this particular part of the cycle. Now as we get to the top here, let's just rotate a little bit more. At this point we could run into a problem, because if we didn't have the split, then the electrons would still be moving in the same direction at this point. However, they'd be then still experiencing a force to the right. Because of the split and because of the change in direction of current, just at the top here, when the split is at the top, that's when current changes direction, and that's when the direction of the forces also changes direction. If it weren't for the split, we would get a problem right at this point where the force would actually stop the wire from rotating. So with direct current, we need this split ring commutator to keep our apparatus rotating in the same direction. In this case, counterclockwise from the point of view of the commutator. And if we just keep this moving, we can see the Lorentz force is constantly changing direction. Now we can also show the current direction. However, this particular applet shows conventional current, which would mean the right-hand rule. So if we apply the right-hand rule right at, let's say, this point, to this section right here, right-hand rule says that the thumb goes in the direction of conventional current, fingers point down, and the force would be as the black arrow represents. And same thing at the bottom, the conventional current would be coming towards the commutator, magnetic field is down, and the force would be in this case as indicated by the black arrow. As long as we have the split ring commutator, this will always rotate in the same direction. Now, one way we can get rid of the split ring commutator is to change our direct current here with a positive and negative terminal. That means it's some kind of battery. We could change that to alternating current. With alternating current, because the current changes direction every particular period of time, usually 60 times a second, then that means we don't have to change the current using the split ring commutator. So with alternating current, you don't need a split ring. With direct current, you do need the split ring commutator.